Hello and welcome back to another video in this series as we learn the basics of Lean in order to write simple maths proofs. Today's video is going to be quite a short one, and it goes almost like a part two to the previous one. So because of that, I'm going to take a more kind of hands-on live coding approach to this one, because a lot of the material was covered last time. But before we dive in, just want to remind you that there is a blog with all the content written up properly. So unlike when I'm talking to you now, the words that I use on the blog are much more carefully chosen, and you can read the code and see the kind of descriptions at your own pace. And also on the blog you can see there's a link to the YouTube videos, which you're probably watching right now. And there's the code on GitHub, which is going to be updated every time I produce a new tutorial. And also the slides, if they're helpful to you, then they're also online as well. So today is Disequality Again. So it's a continuation of what we did last time. So last time we had a hypothesis n is less than 5, and we had a proof objective of n does not equal 5, and we had a lemma, something common knowledge, which was that, oh, by the way, this is and here n is natural, just to be complete. We said that there's a common knowledge that if there are two numbers a and b and one is less than the other, then we can conclude that a does not equal b. And that common knowledge we can think of as a lemma, and we can use this to get from here to here. And what we did last time was we applied this lemma to the goal, and because these things match, it almost builds a bridge. So we want to get there, but this goal matches the output of the lemma, the right hand side. That means that this thing is all we have to prove, because this implies this, so this gets us to here, and this matches our proof objective. So we said when we apply this, it's sufficient to prove this. And in our scenario we had n is not 5 as the objective. By applying this lemma, we had a sufficient proof, a sufficient goal of n less than 5. That's what we did last time, and this was easy because it's given to us by hypothesis. So that's just a refresher of what we did last time. We introduced the idea of using lemmas, and we saw how they could be apply, and then the name of the lemma was, let me see if I can remember it, ne of lt, and there's a kind of a naming scheme that a lot of lemmas conform to. So not equal of less than. So we want ultimately to prove not equal by doing less than. So that was what we did last time. The reason today is almost like a part two is that we've got exactly the same task, but we're going to prove it a slightly different way. So let's work backwards a little bit. Let's rewind this a little bit. And what we're going to do this time is apply it not to the proof objective, but to the hypothesis. That's the new thing. So you can almost see that, well, you can see that this corresponds to this. So if we apply the lemma to the hypothesis, then that matches, and that takes us straight to this. So if my hypothesis n is less than 5, by applying this lemma, it's already given me, it's built a bridge to it's built a building block, the sort of logical step. It's progressed us from a is less than b to a is not b. In our case, n is not 5. So it'll update the hypothesis. So previously it replaced the proof objective. Now it replaces the hypothesis. And then we have a new hypothesis, n does not equal 5, which actually matches our proof objective, so it should be easy to conclude that. Let's look at, there's a nice symmetry there, so let's look at a picture that compares those two approaches. This is on the blog as well. So that's the top half is last week, and this is today's video is the bottom half. You can see the hypothesis and the goal are exactly the same. Last time, and the lemma is the same. So last time we applied the lemma to the goal. We said apply any of LT, and that applies it to the goal. Because the goal matches the right hand side of the lemma, it means that if we can prove the left hand side of the lemma, it takes us to the right hand side of the lemma, which matches the goal. So that becomes the sufficient goal. That's what we did last time. And we were very lucky that actually the distance from the hypothesis to the start of the lemma was not great at all. In fact, it's 0 because it pretty much matches. In other proofs, you might have some other steps to get there. And today we're going to apply that same lemma because the left-hand side of the lemma matches our hypothesis. We can do that. So that builds a bridge forwards, not backwards, but forwards from the hypothesis, which matches the left-hand side of the lemma, which gives us a is not b, which takes us forward. And actually the distance to the goal is minimal because they match already, but in some cases they wouldn't. So that's just a nice symmetry there. And this problem, this simple task, was almost deliberately chosen to illustrate this. Same lemma, same hypothesis, same goal, and we can apply this either to the goal or the hypothesis. So the learning point is that we can apply lemmas to the goal and we can apply lemmas to the hypothesis. That's the learning point. Let me draw a picture just to explain what I mean by a journey to the to the goal or from the hypothesis. So if that's my hypothesis and that's my goal, so some lemmas, if I apply them to the goal and there's a match between the right hand side of the lemma, it means that we've progressed but built backwards. We've built a bridge or steps in this direction from the goal. So now I have to go from the hypothesis just to the left hand side of the hypothesis. So it's made it the journey shorter, as it were. We don't have to go all the way to the end. We can just go here because the lemma gives us the jump to the end, and it does that actually by rewriting the goal to from this to this, and the other way by applying it to the hypothesis. What we can do is, if we have a hypothesis, if you have a lemma which matches the left hand side matches the hypothesis, then it's built a bridge forwards from the hypothesis, and the lemma takes us to the right hand side of the lemma, so that we started here but the lemma takes us to this point. It's kind of progressed us forward, and then we start from here and then can make our way to the goal. So just to summarize that, the application of a lemma to a hypothesis takes us forward, and the application of a lemma to the goal brings the goal kind of nearer to us. So I hope that's kind of clear. So let's turn to code. Let's have a look at the code. what I've done here, this is the online environment, which you can use without installing anything. This was the last tutorial. That's the code for it. You can see n is a natural number. The hypothesis is n is less than 5 there. The overall goal is n is not 5. And we applied this lemma, ne of lt. And if we looked at the info view, before this is applied, you can see the goal is n is not 5. But after it's applied, the goal has changed to n is less than 5. It's pulled the goal nearer to us. And that just happens to be really easy to prove because the hypothesis n is less than 5. So we could apply the hypothesis by saying apply. And because it matches exactly, we can use exact. And that's a good habit if it is exact, because it's more strict and it catches errors earlier, as it were. So this time we've got exactly the same task. So it matches exactly the same. And we're going to apply the same lemma, ne of lt. But how do we say apply it to the hypothesis? Because this will apply it to the goal. So if you can see that. We want to apply it to the hypothesis. There must be a way of saying that's the h is a parameter. That's what we want to point it at. And the way you do it is to say at h. So without an at, it will automatically apply a lemma to the current goal. But by pointing it at h, it then applies the lemma to the hypothesis. So let's see the effect of that. Here, the hypothesis is n is less than 5. That's what we're given at the statement of the theorem. And afterwards, the hypothesis has changed to n is not 5. So this has shown us that indeed the application of the lemma to the hypothesis has changed the hypothesis and taken it from n is less than 5 and taken us a few steps forward to n is not 5. And that just happens to match, you can see there, hypothesis and goal, happens to match exactly the goal. So we can apply that hypothesis to the current goal and it's exactly the same. So we can use the word exact and that completes the proof. So that's kind of neat, exactly the same task, same hypothesis, same proof objective. We're using exactly the same lemma. The only difference is that we're applying it to the hypothesis, whereas here we're applying it to the goal. This is forwards and that's backwards, and the rest of the proof is exactly the same. So it's a nice symmetry there. So I hope you kind of enjoyed that. So we'll just finish with the most important thing to take away, which is lemmas can be applied to goals, and we do that by matching the right hand side of the lemma with the goal. Or we can apply lemmas to hypotheses and the left hand side of the lemma matches the hypothesis. So this takes us forward and the others build a bridge backwards. So that's the main idea. See you next time. Bye.